Hey, hi guys. So today we'll be trying to understand something about asynchronous calls. Uh, why do we need them and how they're different from threads, right? This is going to be a like small playlist of say 3 to 4 videos. Let's start. Today we'll be having some introduction with the definitions and all. We won't be like uh, coding particularly today. I have a drawing pad here. So I'll be trying some stuff and showing things to you. Okay. So what are synchronous calls for first, right? And what are asynchronous calls and why do we need them, right? So of course the opposite of asynchronous is going to be synchronous, which is the normal program behavior flow that we are accustomed to. So we start our main here, and then after the main function, inside the main function we have different function calls as well. In Python we don't have specifically main, but we can think of a like main program flow. Then say we call function f1, right? uh, then we call a function f2 after this. Then we have a say if else condition here. Now the thing is that everything inside this is synchronized, right? So how is it so? F1 is going to execute just after the function may like the program is run, and only then after that we are going to have F2 executed, right? So F2 is not going to execute before F1 or while F1 is running. F2 is going to wait for F1, okay? And whenever there is some kind of waiting for some other thing, we're trying to sync things, right? Sync between things, and that's where the synchronous behavior lies. Each of the nodes inside this program flow graph is synchronized thus, and we can say this is like a normal program flow that is a asynchronous behavior. Now let's try to understand what's the problem with this one, right? So say we have a scenario where we have a piece of code, we want to scrape our websites, right? So this is the main started, and the function scraper function, let's say we have let's say denote with s. It's called with some url1, and it's going to scrape our website with url1, right? And say it takes some 100 seconds, right? Now next up, the same function s takes in another url, that is 2, so we denote it by s2, and it takes up the url and goes on scraping this website, which ideally takes 20 seconds. The next one say takes some 30 seconds, right? Now overall we're kind of getting 150 seconds out of it, right? Now the questions we need to ask ourselves is that, are we really can we do it faster? Firstly, the answer is yes, because our CPU can process like faster than this. It doesn't need 150 seconds to work. So why is it taking 100 seconds here? So this 100 seconds we are not utilizing our CPU first. Some of the time is taken in the network delay, some server response delay as well. The overall latency from the other side is also getting counted here. And on the CPU, like our localhost side, we are just making a call and receiving the data, okay, which shouldn't be taking so much time as 100 seconds. But the problem is that we have to go with this 150 seconds. If we don't change our uh, behavior, like if we don't change the structure of the code, the structure of the code is again synchronous because S2 is waiting for S1. Uh, so they are synchronized as well as S3, S4, S5 up to Sn. So what we can do, right? We can use some asynchronous calls Say we have a main thread and we are calling one S1 here, then we are calling S2 here parallelly. That means we are having simultaneous execution. Okay, then S3. Now say we don't want to have a lot of threads because maybe we run out of RAM. In our case, although we are taking three, in real case scenario, it might take like 3,000 or some 30,000 threads to actually overflow our memory. Okay, so the main fact is that we need to have a upper bound to the number of threads we create. Otherwise, we might end up freezing our computers, right? So after S3, we wait for one thread to finish. Say S1 is finished. Okay, actually S3 was the quickest task in our last case, taking up 20 seconds. So say S3 is finished, right? So S4 comes in and takes its place. And again, we are having some three threads. Say after this S2 gets ended and S5 comes in its place, right? So that's how it goes. And the best part is that what happens basically here, uh, we're using threads. Now the fact is that here S1 is not always working. That is, when S1 is running, the CPU is not getting utilized always. So when S1 is busy in with the network latency, it's waiting for the network to respond. In the meantime, it comes to S2 and works on it, right? So that's how the asynchronous behavior is. We don't need to have S1 and S2 running simultaneously, which will need multi-core CPU. So on CPU 1, S1 is running, and on CPU 2, S2 is running, right? Which we don't want. So what we can do here is that use the threads and increase the processing. So in our last case, we had some, say, 100 seconds here, 20 seconds here, and 30 seconds here. We might end up consuming 110 seconds in total instead of 150 seconds, right? Now this is not a like correct or appropriate calculation. uh, you might ask why 110, why not 100? Because this was 100, and you might think that I am taking the maximum of all of them, but not. As I said, they're not necessarily running on multiple CPU cores parallelly. They might be contained to a particular CPU, and like time sharing the CPU. Okay, S1 is coming first, then S2, then S3, then again S1. So some time might also get taken in switching the CPU, and sometimes maybe S1, S2, S3 are all of them are busy. So that's why we might end up with a bit of more time than 100, right? But the overall thing is that it's reduced than 150 than common batch processing or synchronous task. So I'm talking about threads. Let's try to understand what are threads and why not threads and why asynchronous calls, right? Okay, firstly, the threads are asynchronous, okay, but there is something different between async IO library implementation in Python and the threading. In threading, what happens is that we have our OS here, okay. The OS guy is creating our main program first, and main program is saying, okay, I have two threads to run along with my main thread, that is the actual program flow. So OS comes to know, okay, so you have two more threads, so I'll have to run two more guys along with you. So we have three tasks running here, right? And this two also knows about their address space, the address space of the main. And the overall point is that these things are heavyweight. So can you have something lightweight? Okay, firstly, why these things are heavyweight, right? Because see, creating a process in OS is not that easy. It it has its own data structure inside the OS, because OS needs to know about these threads. So it keeps some certain information about them, and overall it's going to take up a lot of resources on the OS. That's why it might be killing other jobs as well. In this case, we had only three threads, but say in case of like 300 threads we are running, we want to run 300 asynchronous calls. And if we are creating 300 threads for that, we might end up taking a lot of resource just to create it. Okay, we're not working on it. We are not, the thread is not working for now, let's consider. But only to create the structure in the OS is going to take up some resources, a lot of resources actually. Okay, so overall these threads are heavyweight. So what is the way out? The way out are something called coroutines. What are coroutines? So this is the OS, and I run a program, and inside the program I have something called the main event loop, right? This is the data structure for async IO. You can think of it as OS is working for the threads, we have the event loop working for the coroutines. So the coroutines comes to know that there are some asynchronous calls inside the code. The OS is totally unaware of them, right? It doesn't need to handle all of them. It just needs to handle the main program, right? This is the main program, and OS has only one link to this main program. Okay, then inside the event loop we have multiple asynchronous calls which are working parallelly. Okay, now of course these are lightweight because we didn't need a lot of things to get started on each of the asynchronous calls. They are like very much like the normal function calls, but we are just having them in asynchronous, right? And also it's getting handled by this something called this event loop, right? Which is kind of important. We'll discuss more about it in the later part of the tutorial. So I'm not writing it over. It's basically event loop, right? And the last question that I want to answer is that um what like, is there any uh, drawback of this coroutines? Yes, I'll say. If you have a multi-core CPU, firstly, coding asynchronous stuff is a bit difficult. Okay, you have to make the structure. In case of threads, threads might run on like multi-core CPU faster than this ones, right? Because here it's each time working on any one core of the CPU, right? These asynchronous calls cannot work on multiple CPUs. Okay, so that's the drawback. We can't have parallelism using the coroutines, but can't we design? Yes, we can design. How we can do that? Say we have two CPU cores, right? Now what we're doing is that we have a main created from here. Now inside the main, we create another thread, and the thread one is running basically on this CPU, and the thread 2 is running on this CPU, right? So they are parallel. Now I create two asynchronous calls, right? So say I have asynchronous calls over here as well as here. Now these ones, these three calls, each other are asynchronous but not parallel, and so are these four, right? But this one is parallel to this one, this event loop. So we have basically two event loops here, and each of the event loops are handling their own asynchronous calls, their own coroutines, but the event loops are parallel because they are working on multiple CPU cores, right? So that's how we can code things up for multi-core CPU as well. And we can have a like robust structure with the coroutines, right, without taking up too much space. And the best part is, in case of threading, you don't really get to utilize your CPU when your CPU is single core. So in case of single core, one thread will run for some time, the other thread will run for some time. Okay, but in case of the coroutines, if we have a single core CPU, they're understanding that they will detect that which uh, one asynchronous call is not taking up so much time or taking up some time, and they will try to utilize that time gap between the for each of the coroutines. So if one coroutine is sleeping, let's try to work on the other coroutine. That's where the difference is. Okay, so coroutines are designed to work on single core CPUs, but we can also make them work using the thread on multi-core CPU. While threads, you can't really like utilize or accelerate the process using the single core. So if it is a single core, it's just going to run as a normal program, although it is asynchronous, but it's not helping me. But in case of asynchronous calls or coroutines, we might end up having the process accelerated overall. So that's it that's it for today. We'll try to code up something in the next videos. Okay, take care, goodbye till then.